bachelor's in mathematics from North Dakota State University. Oh, Isaac. Dr. Fries moved to the Boston area soon thereafter to attend Northeastern University. Good school. That's where I got my Bachelor of Science degree. Dr. Fries received his PhD under the advisement of Dr. Jerzy Wyman, a pillar in the field of representation theory and algebraic geometry, with a thesis titled Standard Basis for Coordinate Rings of Cotangent Variables. 4 years ago, Dr. Fries joined the ENC community. He has since been credited for his new approach to pedagogy and the unique nature of some of his math classes. So some students will tell you these classes are hard, but that might be a good thing. He has recently offered special math classes in the area of cryptography and differential geometry, and continues to work on several future classes and projects in conjunction with the physics and engineering work. So, without any further ado, welcome Dr. Fries.
So, my goal in the lecture today is to try and just give a gentle, i.e. computational introduction to some of higher mathematics, and try and maybe just give you a bit of the flavor of what it is that I'm trying to do. And where we're going to start is a structure called SL2. And, well, any good math presentation begins with a definition. So SL2, and we usually put C here, or you can talk about R, whether it's over the complex numbers or the real numbers, is the set of all matrices, A, B, C, and D, with the condition that A plus D has to be 0. So really we could rewrite this as all matrices A, B, C, minus A, and there's no other conditions. So the trace, or the sum of diagonal elements, has to be 0. Up until now, we're just talking about matrices, but what makes this different is the following thing. Well, first of all, we can add two matrices at this form. And we end up with a matrix that has the same property. Diagonal entries add to 0. But the thing is, we can't multiply them. So if you have two matrices such that the diagonals add to 0, their product isn't 0. So F takes me this way, and I multiply by D minus I. So here I multiply by D. F takes me this way. I multiply by D minus 1, D minus 2. Coming in here, I multiply by 2. Here I multiply by 1. And here, where do I go? So if I differentiate y with respect to x, I get 0. I go off to 0. So that's what F does. We can throw in the action of E. Remember, E moved me to the left and multiplied by I. So in this case, here's E, I multiply by D. I multiply by D minus 1. Here I multiply by 3. 2, 1, and I head off to 0 when I halfway. And lastly, I need to put in the actions of H. It turns out you can call that E3 if you want. And it corresponds upper right. But you can compute everything just from the equations that I've already given. So, how do I determine actions of SL3 in 2 minutes? Well, the big thing to realize is I have two H's now. Right? I have two things that are kind of diagonal matrices. So I'm not going to just have a single. Well, I mean, what does it mean to be a highest weight vector for SL3 now? So if I have an SL3 module, so you just, the definition that I gave for SL2 modules, just take the same definition for SL3 modules. Not much changes. But what is a highest weight vector or element for an SL3 module? So M in M is a highest weight element. Of weight, and here's the thing, we need to specify two numbers. We'll take mu and lambda. If, well, we now have four conditions. E1 on M is 0. E2 on M is 0. H1 on M is mu times M, and H2 on M is lambda.